Today we're going to learn about the geometric mean, particularly in geometry, and how it can be used to find lengths using similarity and right triangles. When you hear the word mean, the first thing you probably think of is average. But a normal average, a normal mean, is when you add up the numbers and you divide by the number of numbers. This is different, although you can kind of draw a parallel in that if I give you two numbers and ask you to take the average, that's the mean, uh, the, the average will be the number in between those numbers. If you just have two numbers, the mean is right in the middle of those two numbers. The geometric mean is also in the middle between two numbers. It's located in a geometric sequence. A geometric sequence is a sequence that is created by multiplication. That's all it means. You're multiplying by the same number repeatedly. From 3 to 6, we're multiplying by 2. From 6 to 12, we're multiplying by 2. 12 to 24, by 2 again. That 2 is called the common ratio. Notice if I pick any number in the sequence and I divide by the previous number, I get that 2. The geometric mean is visible in the geometric sequence because if I pick any three numbers and I multiply the outside two, what I get is the number in the middle. Notice this isn't a normal average. You're multiplying the numbers. When you take an average, you add the numbers. So if I multiply the outside numbers, I get the number in the middle. Take a look at 3 and 12. 3 times 12 is 36, and the square root of 36, look at that, it's 6. If I pick three numbers like 6, 12, 24, and I multiply the 6 and the 24, I get 144. The square root of 144 is 12. There it is. That works anywhere in the geometric sequence. Pick three numbers, multiply the outside two, take the square root, and you get the number in the middle. 24 times 96, 2,304. The square root of 2,304 is 48. In general, then, you just need to know that to find the geometric mean, you multiply the two numbers and then you take the square root, and that number is the geometric mean. The geometric mean is what you get when you solve a proportion that has x's in one of the diagonals. Show you what I mean. If I were to solve for x in this first one, x over 4 equals 16 over x, I would cross multiply. X times x is x squared. That would be equal to 4 times 16. I'm going to write that out, 4 times 16. And then to solve this, I would take the square root of both sides. Notice, you're multiplying the two numbers and you're taking the square root. This is the square root of 64, and your x then is 8. Look at the other proportion. I'm going to cross multiply. X times x is x squared, and that equals 9 times 16. And I'm taking the square root of both sides. And again, observe, you're multiplying the two numbers. That's the product. And then you're taking the square root, and it's the positive square root. This then is the square root of 9 times 16 is 144, and x would be 12. The geometric mean of 9 and 16 is 12. If I just ask you to find a geometric mean, though, all you need to do is multiply the two numbers and take the square root. What's the geometric mean of 8 and 32? Take 8 times 32, put it under the square root. 8 times 32 is 256. This is the square root of 256. And the square root of 256 is 16. The geometric mean of 8 and 32 is 16. The geometric mean occurs several times When I take a right triangle, that's triangle ABC, and from the right angle, I drop a perpendicular. There are three similar triangles here. Look at the triangle that is created on the left side. I'll highlight it in red. This triangle here. It's similar to the big triangle, triangle ABC, because you have angle-angle similarity. Let's figure out where that is. Notice that the big triangle, triangle ABC, at the very top has a right angle right up there at B. Notice the small triangle in red, triangle ADB, has a right angle also down at the bottom. So they both have right angles. Notice the big triangle, triangle ABC, has angle A. Notice the little triangle also has angle A. So what we know then is that they have two angles congruent. That's angle-angle similarity. Because if two angles congruent, the third angles are congruent because we only have 180 degrees in each triangle. So they are similar, and we're going to write the similarity statement. This is triangle. We know that A has got to be congruent right here to itself. Line up the congruent angles. We see that in the big triangle, there's the right angle at the top, angle B. The right angle in the small triangle in red is down here at D, right there. So angle B and D, that's a right angle, and D is a right angle. So look at the triangle, triangle AD, the only point left is up there at the top, B. So we know that C would be congruent to B in those two triangles. And the triangle on the right side, which we'll highlight in blue. So this triangle is also similar to the big triangle. All right, so this one in blue, we see that it has a right angle down there at the bottom at D, the triangle in blue. We see that it also has angle C, just like the big triangle, triangle ABC has C. So the big triangle ABC has a right angle at the top at B, and it also contains C, like the triangle in blue. Therefore, we have angle-angle similarity. Let's write the similarity statement. Now we're looking at triangle ABC as we do this. So forget the one in the middle for a moment. Okay, in blue, we know that the right angle in the big triangle, ABC, is at B. It's in the middle. So I know that in blue, the right angle is at D. It's going to be in the middle. The right angle is in the middle in both of these. I need a point in front of that. I know that C in the big triangle is congruent to itself. I'm lining up the congruent angles. The triangle in blue also has C. So C has to be third, just like it is in the first statement. And look at the triangle in blue, D and C. The only one left is B. B has got to be first. That means angle A has got to be congruent to angle B. Since both of these triangles are similar to the big triangle, they're all similar to each other. They all have the same congruent angles. What we need to do then is take those three triangles out and put them in the same position so I can easily tell which sides correspond. I could use the statement here, the similarity statement, to do that, but it will be much easier if I have the picture and I can just look and easily see which sides correspond. So let's move these things around. So I flip the one triangle, rotated it. Notice how the right angle is at D, just like it was on the previous page when I marked it in blue. I'm talking about this triangle right here. The right angle is at D, and C the triangle's been flipped over, but C is still that one angle there. And right up here is B, and it's down there since I flipped the triangle. Now we'll move that over here out of the way. It's a bit smaller than that other triangle. It was contained within it, remember? Then the small triangle, triangle ABD, I'll need to flip it too. I flipped it. Now I'll rotate it and move the points in position. And here I've put angle D. Again, notice it's the small triangle we're talking about right here. I flipped it, and the right angle's still at D, and A is still itself there, and B is where that small angle is, up at the top, right there. Here are the three triangles set up so that we can easily tell which sides correspond. Notice that we did this all correctly because look at the first part of our similarity statement. Triangle ABC. ABC. It's similar. Let's actually look at this one next here. BDC. BDC. Notice how they're in the same order? We've done it correctly. And that's similar. Again, look at ABC right here. ABC. Notice the order in the top big triangle. And look at the bottom triangle. Same order. ADB. We can tell we have things lined up, and now we can easily make statements just by looking at the triangles. Take a look at the top two triangles. I'm going to set up some proportions that allow us to solve for some lengths that we need. BC, it corresponds with this one, DC. As, go to the bottom one here, AC corresponds with this one here, BC. BC is to DC as AC is to BC. Let's cross multiply this. BC times BC is BC squared, and that equals DC times AC. Look at the top triangle and the bottom triangle. I can see that AB, it corresponds, the AB is right here, to this one, AD, as, there we go again, AC is to the bottom triangle, AB. I'm just lining up corresponding sides. Cross multiply that, and you get AB times AB, AB squared, equals AD times AC. For our last proportion, we're going to look at the bottom two triangles. BD, that one, is to this one, AD, as DC is to DB. Now, I'm not going to write DB, I'm going to write BD. The order you put the letters in your segment makes no difference, but I'd rather write BD instead of DB. You'll see why if you look. It's to make it a little more obvious when you multiply. Those two are the same. Whether you write BD or DB doesn't matter. It's still BD times BD, which is BD squared, equals AD times DC. Remember that idea of the geometric mean? The geometric mean is the square root of the product of two numbers. Notice that BC, if I solve for it, I have to take the square root, is the square root of DC times AC. In other words, the length BC is the geometric mean of DC and AC. And the second statement, If I solve for AB, I have to take the square root of both sides, and AB ends up being the geometric mean of AD and AC. And if I solve for BD, I take the square root of both sides, and then it's BD, and it ends up being the geometric mean of AD and DC. Each of those lengths is the square root of the product of two numbers, in this case, segments. BC and AB and BD are the geometric mean of those segments under the square roots. To make this a little bit easier to work with, I put some lowercase letters in there to represent the lengths of each of those segments. So AB is little a, BC is little b, AD is x, DC is y, I'm calling BD h, and AC, the whole hypotenuse of the big triangle, I'm calling little c. Let's go to the top statement here. BC squared, look at the picture, BC squared, I'm calling that b squared, equals DC, look at the picture, DC is y, times AC. AC is the whole hypotenuse of the big triangle, it's little c. Look at the second statement. AB squared, that's a squared, it equals AD, notice that's x, times AC, and AC again is the hypotenuse of the big triangle, triangle ABC, it's little c. And the last one in blue, BD squared, that's h squared, that's the height inside there, equals AD, which was x, times DC, again, look at the big triangle, DC is y, and these are the statements we're going to use. As you look at these, notice that little c, that's the whole segment AC in the big triangle, y. I have to add those two together to get little c, because you're going to use this in a bunch of questions. You've got to recognize that little c, I must add x and y together to figure it out. Now look at those three statements and notice that there's just a pattern that you're following. B squared equals the piece on its side, that's y, times the whole hypotenuse of the big triangle, c. B squared equals y times c. And the next statement, the second one, is the same pattern on the other side. It's that leg squared equals the piece of the hypotenuse on its side, x, times the whole hypotenuse, c. The leg squared equals the piece on its side times the whole hypotenuse of the big triangle. And the last one, with the h in it, h squared just equals x times y. Study those, look at the pattern, look at the picture, and memorizing these is much, much easier than trying to use similar triangles in this diagram. Using similar triangles is very difficult because it's hard to tell what corresponds. But using this, you can do these questions very, very quickly. Here's an example of how to use those cross multiplications to find the different lengths in this right triangle. Let's find x. The pattern was the leg squared, x squared, equals the piece on its side, that's 4, times the whole hypotenuse, that's 4 plus 6, which is 10. That means that x squared equals 40. And I'm going to square root both sides to find it. And we're going to simplify these roots. Your answers on this assignment, there'll be a bunch of roots. We know that 40 is 4 times 10. Remember, we take the largest perfect square out of 40, which is 4. 4 times 10. I can take the square root of 4. It goes out front of the root, which is 2, and it's 2 root 10, or you could say 2 radical 10. Exactly the same pattern on the other side. The leg squared, that's z squared, equals the piece on its side, which is 6, times the whole hypotenuse of the big triangle, which was 4 plus 6, 10. These two are the same exact pattern on each side. The leg squared equals the piece of the hypotenuse on its side times that whole hypotenuse. I'm talking about the hypotenuse of the big triangle. This would be z squared equals 60. I'm going to find the largest perfect square in 60, and it's 4. 4 times 15. I can take the square root of 4. That would be 2. And 2 radical 15, or 2 root 15, is my answer. And the last one, let's find y. It's y squared. That's the height squared of the big triangle, equals these two pieces multiplied, 4 times 6. That becomes y squared equals 24. We square root both of those to find y. And the largest perfect square in 24 is 4 again. 4 times 6. I can take the square root of 4. It's 2 that goes out in front of the root. 2 root 6 is my answer for y. What is the geometric mean of 500 and 12,500? You definitely need a calculator for this. The geometric mean is the square root of the product of two numbers. You multiply them and take the square root. The answer then is the square root of 500 times 12,500. Make sure you use parentheses if you punch it in like that. You can use Desmos, desmos.com. You're going to end up getting 2,500 as your answer. Question 2. What's the geometric mean of 32 and 128? Just put in your calculator 32 times 128 and take the square root of that, and you get 64. Question 5. Write a similarity statement comparing the three triangles in the diagram. Triangle XTC. X is where the right angle is in the big triangle. So this is the right angle, that's X. And that will help us figure out in the other triangles where things go. XTC. Let's go with the triangle on this side. The right angle is at Z. So Z and X would both be first. And I know that T corresponds with itself. See how T is second there? It's going to have to be second here because it's congruent to itself. And then the triangle on this side is ZTX. Now let's do the small triangle over here. Remember, the right angle in the big triangle was at X. The right angle in this small triangle is right here. So X in the big triangle corresponds with Z in the small triangle. X is first, Z will be first for that small triangle on this side. I know that C corresponds with itself. You see how C is the third point in that big triangle? It's going to have to be third here because C is congruent to itself. That means the point we're missing, let's see, we got ZXC. X has got to be in the middle. Here we have the same picture, but in a different configuration. It's flipped over. I'm not sure if the triangle is exactly the same, but it's the same procedure. Look at the big triangle, ZJB. Notice that the right angle is at Z again. That's my right angle. That means let's start with the small triangle. The right angle in the small triangle is there at H. So Z and H would have to be first. I know that J corresponds with itself and J is second. It'll have to be congruent to itself. It's in both triangles. So that small triangle is triangle HJZ. Now let's do the triangle on the right side, triangle ZHB. Put everything in the right order. Always go back to the big triangle. It's easier to figure out that way. I know that the right angle's at Z. We figured that out right off in the big triangle. The right angle's at H in the triangle on that right side. So H has to correspond with Z. I know that B is congruent to itself. See how B is third in the big triangle? That means it's got to be third in that last triangle we're working on. And the triangle was H something B, HZB. Question 10, applying all that stuff we learned about similarity and right triangles. X, that's the leg of the big triangle, is x squared, it's the leg squared, equals the piece on its side, which is 8, times the whole hypotenuse of the big triangle, which is 14. We get x squared equals, calculator, 8 times 14 is 112. I need to find the largest perfect square in 112. I see there's a 4 and 8, and there's another 2, because 8 is 2 times 2 times 2. There's also another 2 and 14. That's 2 times 7. So there's 4 2's in 8 times 14. 3 of them in 8 and 1 in 14. 2 times 2 times 2 times 2 is 16. This is 16 times something. If you have a hard time with this stuff, make a list of perfect squares. That's 4, 9, 16, 25, 36, any number times itself. 49, 64, 81, 100, and they keep going. You can Google a list if you like. See, 11 squared is 121, 12 squared is 144, and that's enough for now. 112 divided by 16 is 7. 16 times 7. Yeah, it was right there, wasn't it? That's under the square root because we're going to find x. X then equals, the square root of 16 is 4. That's 4 root 7. 4 root 7 is what x is. Simplest radical form is what we're after. Let's find z. Z is the same pattern. The leg squared equals the piece on its side, that's the 6, times the whole hypotenuse, which was 14. 6 times 14 is 84. You get z squared equals 84. We're going to take the square root of both those to find z. There's a perfect square in 84. I'm sure 4 divides into it. Let's divide it by 4 and see what's left. 84 divided by 4 is 21. 21 does not have any perfect squares in it. It's 3 times 7, and both of those are prime. The square root of 4 is 2. 2 root 21 is my answer for z. Now let's find y. Last pattern. These two are the same pattern. The leg squared equals the piece of the hypotenuse on its side times that whole hypotenuse of the big triangle. The last one is y squared, that's the height, equals these two pieces multiplied. Y squared equals 8 times 6. You get y squared equals 48, square root, square root. Now, the first thing you might try is 4 times 12. But I want to point out there's still a perfect square in 12. 4 divides into 12 again. This is 4 times 3. And since 4 times 12 is 48, and 12 is 4 times 3, those two perfect squares, if you multiply any two perfect squares, you get another perfect square. 4 times 4 is 16. What I have then is the square root of y squared equals, and 48 is actually 16 times 3. Square root of 16 is 4. 4 root 3 is my answer then. Question 13. I want to point out what happens when you square a root. If I take the square root of 8 and square it, it's root 8 times root 8, which, by the way, is root 64. And the square root of 64 is 8. The square root of 5 squared is root 5 times root 5, which is root 25. And the square root of 25 is 5. Now you're going to notice something here. When you square a root, they cancel each other out. They're in fact inverses of each other. As I do number 13, I need to find one of those three cross products that allow me to find a variable. And the only one that can work is these three pieces. I know the height squared, that's root 133 squared, equals these two pieces multiplied, x times 19. And when I square a square root, they cancel each other out. This is 133 equals x times 19. I can find x by dividing by 19. I hope this divides evenly. And it does. 133 divided by 19 is 7. X is 7. Let's take and replace x with 7. Now I have everything I need to find z and y, because I know the leg squared, z squared, equals the piece on its side of the hypotenuse, 7, times the whole hypotenuse, which is 7 plus 19, 26. 7 times 26 is 182. Z squared equals 182. Square root, square root. This is a tough one, but I want to point out you can tell right here that there are no perfect squares in 182, because 26 is 2 times 13. So that means z squared equals 7 times 2 times 13. Those are all prime numbers. There's no perfect squares anywhere there. Nothing times itself. The square root of 182 is what z squared is. And now y, the pattern was the leg squared equals the piece on its side, that's 19, times the whole hypotenuse of the big triangle, which is 7 plus 19, which was 26. 19 times 26 is 494. And again, we can tell right here that there are no perfect squares in 494. 19 is a prime number. The only factors of 19 are 1 and 19. 26 is 2 times 13. And 19 times 2 times 13, there's no perfect squares there. No number times itself. So when I take the square root of both sides, there's nothing I can do with that. And this is just the square root of 494. Question 15 is a lot like the last one. We just have a different kind of root here. Let's point out, let's take an example, what happens when you square something like 4 root 2. Let's square 3 root 7. If I square 3 root 7, that is 3 root 7 times 3 root 7. I can multiply those whole numbers, 3 times 3, that'll be 9. And I can multiply the two roots. Root 7 times root 7 is root 49. I can't multiply these two because one's a root and one's an integer or a whole number. There is times right here, though. When you say 3 root 7, it's 3 times root 7. Look at root 49. 49 is one of those special numbers. It's a perfect square. Square root of 49 is 7. No root. Square root of 49 is 7. This is 9 times 7, which is 63. 3 root 7 squared is actually 63. One more example. 2 root 5 squared. That's 2 root 5 times 2 root 5, which is 2 times 2, 4. Multiply your two whole numbers, your two integers. And root 5 times root 5 is root 25. Again, there's times there. Square root of 25, I can work out. That's 5. This is 4 times 5. No root. When you take the square root, the root's gone. 4 times 5 is 20. 2 root 5 squared is actually 20. Check it on a calculator. Just like the last one, I need to work with one of the variables that has enough segment lengths to find that variable. And the only one that can work here is the x. I know that the height of the big triangle squared, 4 root 2 squared, is equal to these two pieces multiplied, 4 times x, or 4x. 4 root 2 squared is 4 times 4, 16. Root 2 times root 2, root 4, equals 4x. This is 16 times the square root of 4. I can take the square root of 4, it's 2. This is 16 times 2. Again, no root. Once you take the square root, the root is gone. 16 times 2 is 32. 32 equals 4x. We can divide by 4 and see that x is 8. Let's replace this x with 8. Now I can find either of the two legs. Let's start with z. The leg squared, z squared, equals the piece on its side, which is 4, times that whole hypotenuse, which was 4 plus 8, 12. Z squared equals 48. Hey, we just did this on a previous page. Remember how it was 4 times 12, but there was another perfect square in 12 of 4. 4 times 3 is 12, and 4 times 4 was 16. If you multiply two perfect squares, you get another perfect square. So it's 16 times 3. That's what 48 is. And the square root of 16 is 4. 4 root 3 is what I got there then. So z is 4 root 3, and x was 8. All right, let's find that y. Same pattern as with the z. The leg squared of the big triangle, y squared, equals the piece on its side, that's the 8, times the whole hypotenuse of the big triangle, which was 12. 8 times 12 is 96. Y squared equals 96. And I'll square root both sides. We're going to find a perfect square in 96. Of course, we can guess and check. We can start looking for numbers, 4, 9, 16, 25, and use our calculator and guess and check. But we can actually look up here and figure out that perfect square. You see, 8 is 4 times 2, and 12 is 4 times 3. I'm looking for something times itself. And hey, those two 4s, 4 times 4 is 16. I'm betting 16 divides into 96. In fact, it ought to be 16 times 6 because 2 times 3 is 6. Let's check. 96 divided by 16, look at that, it's 6. Here's 16. It is 4, and 4 with 6 is my answer for y. This one's very close to the last one. Instead of 4 root 2, we have 2 root 2. Same procedure though. We need to find x first because we have 2 root 2 and 8, and x is the only variable I can find right off. It's the height of the big triangle squared, 2 root 2 squared equals x times 8, or 8x. 2 root 2 squared is 4 root 4. I'm squaring them both. 2 times 2 is 4. Root 2 times root 2 is root 4. Equals 8x. Square root of 4 is 2. This is 4 times 2. So 8 equals 8x. Divide both sides by 8, and x is 1. Let's erase x and put a 1 there. Now we can find either z or y. Let's start off with z. The leg squared, z squared, equals the piece on its side, 1, times the whole hypotenuse, which is 1 plus 8, 9. Z squared equals 9. Hey, I like that. Square root of both sides, and z is 3. On the other side, the leg squared, y squared, equals the piece on its side, which is 8, times the whole hypotenuse, which is 9. Y squared equals 72. Let's look for that biggest perfect square. We know 9 is a perfect square. 9 divides into 72, but look at 8. 8 is 4 times 2. And 4 times 9, both perfect squares, make a larger perfect square. 36 is in 72. 36 times 2. Square root of 36 is 6. So y is 6 root 2. Question 17. Just like the previous two, we need to find a variable that has enough values to make that product that allows us to solve. And the variable we can find is z. Remember, the leg squared times the piece on its side equals the whole thing, which, by the way, is z plus 20. Let's write that down. 2 root 145 squared equals the piece on its side, 20, times, now I'm going to need parentheses here, let's not use a dot, 20 times z plus 20. The leg squared equals the piece on its side times the whole hypotenuse. This is going to be 4 times 145. Remember, there's times here, and 2 squared is 4, and when I square a square root, they cancel each other out. This is equal to 20z distribute plus 20 times 20 is 400. 4 times 145 is 580 equals 20z plus 400. We'll take a 400 off each side. This is 180 equals 20z. And divide by 20. And it looks like z, 180 divided by 20, is 9. Let's replace the z variable with 9. Let's find y. The leg squared, y squared, equals the piece on its side, 9, times the whole hypotenuse, which we now know is 29. And I'm going to leave it just like this, because 29 is prime and 9 is a perfect square. Square root of 9 is 3. 3 root 29 is what y is. Let's find x now. It's the height squared of the big triangle. X squared equals these two pieces multiplied. 9 times 20. 9 times 20 is 180. X squared equals 180. And I'm going to square it. And I need the largest perfect square in 180. Up here we can see 9 is a perfect square in 180. But 20 also has a perfect square in it of 4. 20 is 4 times 5. 9 is a perfect square, and 4 is a perfect square, and 4 times 9 is 36, another perfect square. 180 divided by 36 is going to be 5. This is 36 times 5. I can take the square root of 36. That would be 6. 6 root 5 then is my answer for x. Question 20. The values we can work with are the 589 and the 19. That means I can find z because the leg squared is equal to the piece on its side times the whole hypotenuse of the big triangle, which is z plus 19. That's root 589 squared equals the piece on its side, 19 times the whole hypotenuse, z plus 19. A square and a square root cancel themselves out. Remember how the square root of 9 squared, root 9 times root 9 is root 81, but the square root of 81 is 9. When you square a square root, the square root just disappears because they're inverses of each other. A square and a square root effectively cancel each other out, meaning that this is 589. We'll distribute, take the 19 to both. 19 times z is 19z. Plus 19 times 19, let's see, 19 squared is 361. We'll solve for z. We'll take a 361 from both sides. 589 minus 361 is 228. 228 is 19z. Divide by 19. And 228 divided by 19 is 12. Let's replace z here with 12. Now we can find y. The leg squared equals the piece on its side, 12, times the whole hypotenuse of the big triangle. 12 plus 19 is 31. 12 times 31 is 372. Look up above here and we can figure out a perfect square. 31 is prime, there's nothing there, but 12 has a 4 in it. It's 4 times 3. So we know 4 divides into 372. If I divide it by 4, I get 93. So when I take the square root of each side, I'm going to write 4 times 93 in there. 93 doesn't have any perfect squares. It's 3 times 31. Those are both prime. Y then, the square root of 4 is 2 root 93. Or you could say 2 radical 93. Z was 12, and Y was 2 root 93. All right, this last length here, X, the way it works is X is the height of the big triangle. X squared equals 12 times 19. 12 times 19 is 228. 19 is prime, that's in 228, but 12 is 4 times 3, which means we know 4 divides into 228, and the rest of it, 3 times 19, there's no perfect squares in there. 4 is going to be our biggest perfect square. If we divide that by 4, we get 57. So when I take the square root of both sides, I get 4 times 57, and the square root of 4 is 2. 2 root 57 is my answer for x.